Hi, welcome to another edition of Linear Algebra. Today we are going to continue our conversation about spanning sets and linear combinations. So let's go ahead and see the list of topics that we had here for this section. We started talking about linear combination, and then we mentioned how to figure out if a vector is a linear combination of some others. We defined the span of a set. We talked about spanning sets of Rn. We talked about span of two vectors in R3. So we have come to the issue of linear dependence versus linear independence and some of the ideas that are connected to that. So let's go ahead and start by an example. So dependence versus independence. What is that about? Let's take an example and then we're going to come down to the definition. Suppose I give you a problem and ask you to describe all linear combinations of each set. Instead of all linear combination, you remember that the short word for all of that was the word span. All linear combinations of elements of a set is referred to as span. So I'm asking you to find the span of this thing, span of this. And here's another question, span of this one. And here's another one, span of this one. Well, you look at these three assignments, you see that the first two vectors is the same in all three of them. This one, that's it, two vectors. This one, there's an additional vector here, 264. I wrote it in red so it stands out. This one has an additional vector 5, 5, 3. So all linear combination, that's what we want to create, which means like I want to multiply this thing by A, multiply that one by B, and add them up for all possible A's and B's. What am I going to get? So I get something here, something here, something here. The question is, how do we compare them? Well, if you look at these vectors that are added to these things, you see that this 264 has a relationship with some of these vectors that I have here, or was in the original set. It's rather obvious connection. What's the connection of this red one to the two vectors that were there to begin with? So you want to pause this thing for a second and discover this by yourself. That's the clue of this problem. Do you see the connection? So well, of course, the connection is that this is just the double of that. Okay, so here, if you want to making all the linear combination, if you're making a combination of 1, 3, 2, and then B times 4, 2, 1, here you're making all linear combination. Let's say A times 1, 3, 2, B times 4, 2, 1, and C times 2, 6, 4. You might say, wait a moment. Why are you doing like this? This can be written, factor a 2 outside and becomes 2C times 1, 3, 2, and then combine these two together. So you'll have A plus 2C times 1, 3, 2, and then tag along what the other one was. So what you are building here is not different from what you were building over there. That is, if you consider the set of all possibilities here, set of all possibilities there, these two sets will be exactly the same, because whatever you can build out of 1, 3, 2, you can also build the exact same thing out of 1, 3, 2, and 2, 6, 4, and vice versa. Whatever you have out of these two, you can build out of one of them. So there is no additional advantage in terms of creating new elements by having this thing here, because it was already there. That's not opening a new road to you or new elements to you or anything like that. It's just making the set more crowded. You are creating redundancy in your system, and that redundancy perhaps in some engineering application might be a good thing. Mathematically speaking though, whatever you were creating out of these two will be exactly the same thing that you will be creating out of these three. How about the example C? Same issue here. Can you see there is a connection between this red one and the black ones we had over there? Again, I want to encourage you to take a moment and look at this thing yourself. So here's your cue for pausing the video and trying to find for yourself. In what sense is this thing redundant? This red one, you can build it out of those two, and if your idea is to build all the linear combinations, there is no reason to include this. Why is that so? Because this is simply the sum of these, and you are creating all the linear combinations including that particular sum, so this does not fatten your final output. There is nothing extra that's going to be created out of presence of this that wasn't already being created out of these first two. So it is in this sense that we say this set of vectors as a collection. As a collection, it's a dependent set. That there is an extra in it that you can remove. This is also a dependent set. There are vectors in it that are already a linear combination of the other ones, and if you eliminate them, the overall span is not going to be hurt. Nothing is going to be missing. So the designation that we are going to make here is that this vector, this set is going to be called the dependent set. Okay, the property of dependence or independence is a property of a collection of the entire set. If there are redundant elements in that set, then you call the set dependent. If, for example, here you might have the intuition right now that this is not dependent, this is not a multiple of that, this is not the multiple of this, there's no connection between these two. Actually, we have looked at this thing before. If you have two vectors, they have to be parallel to each other for them to be dependent, and this is not the case. Here, this collection of vectors, we are going to call it independent. Okay, so that's the distinction between dependent and independent. So it's kind of like the everyday usage of these two words in English as well. If you copy your style of attire or something out of what the other people do, so you're dependent on what they do, and you're essentially following the fashion of other ones. If what you're doing has nothing to do with what the other people are doing, then you're independent from them. Okay, so the language terminology is somewhat similar. Okay, what is the definition of these, mathematical definition? There are two definitions for these concepts, and they are very closely related to each other. Let me express both of them. So suppose we have a collection of vectors. Just for example, I'm going to write maybe say 4 of them, but it's good for any collection of vectors. Suppose we have a set of vectors. Let's call them, say, U, V, W, and say maybe another one, say what's another one, say t. We say the set is dependent if one of the vectors is a linear combination of the others. So if one of them is built from the other ones, well, which one? Well, it depends on the particular problem that you have in mind. Perhaps V is some sort of a combination of U and W and T. So it could be that V is some combination of, now we don't know exactly what numbers involved in that problem, something times U plus something times W plus something times T. Or perhaps it is the W that's a linear combination of the rest of them. Perhaps W is a linear combination of, say, U. So question mark, I'm putting for whatever multiple you have here. Any number would work. So for example, if you had 2 and 3 and 4 and say 5 and 11, so 11 WU and V and say 7T or whatever. So whatever coefficient shows up, it depends on the problem that you have in front of you. But if any of these vectors is a linear combination of the rest of them, then you call the whole collection a dependent collection. Now the fact that we have one of them stand out on one side and everybody else on the other side, and the fact that you can choose this thing in many different ways, kind of makes the definition a little bit not the optimal choice to use here. So that we have another definition. So definition 1, definition 2, if there are 4 numbers let's call them, say, A, B, C, D, like 2, 5, 7, 11, or whatever it might be. If there are 4 numbers, now I'm going to put some fine print here that I'm going to come back and fill it up. Let me see if you can fill it up yourself. If there are 4 numbers such that first number times U plus second number times V plus the third number times W plus the fourth number times T is equal to 0, then we say the set U, V, W, and T is dependent. So again, let me see if I can prompt you to help me here. So it's where you wanna. I need to put a little bit of fine print here so that we don't go for the easiest answer, or the so-called trivial answer. If there are 4 numbers such that this is 0, there is an easy choice of A, B, C, D that makes this thing 0 regardless of who is U, V, W, and T. Okay, what can I put here to make this thing 0? Of course, I can put all of them 0. This is always going to be 0. And regardless of what vectors we have, we are going to call them dependent. Of course, that is not going to be a useful definition. So what should I put here? Not all of them 0. So we are not doing a cheap trick answer or something, not all zero. If there are four numbers such that they are all not zero and this whole thing is zero, we call the collection of vectors dependent. Now how is this same as that? Well, bring all of these ingredients to one side. So for example, you had 2u, so write 2u here and then put your v next to it, and then 3w minus 4t is equal to 0. So if you have the equation with one of them in terms of all the others, well, if you take everything and put it on one side, it's going to have this character to itself. It's going to have this style to itself. So this style and that style is zero, are the same. So how is that make sure that we are not picking all of them to be zero? Well, the one that is picked to be on the left hand side, the coefficient of that is, the way in that style is always 1, so we are guaranteeing that we are not doing the cheap equation. We are not saying 0v is equal to 0u plus 0w plus 0t. That's a trivial statement. That's just saying 0 is equal to 0. Aside from that, can you make a connection between these vectors? Aside from the trivial connection, can you find out a connection between these vectors? If you do find such a thing, then they are dependent. And what's the other side of the coin? If there is no A, B, C, D that other than 0 that makes this thing 0, then we call the collection independent. So the other side of the coin is the following. We call U, V, W, T an independent set if there is no possibility for AU plus BV plus CW plus DT to be 0 other than the trivial choice of picking a 0 multiple of each of them. Okay, so a little bit of a subtle definition. It's a little bit of a tongue twister there, but it is easy to master after a few exercises. So let me ask you some questions. So here I write some vectors and you tell me, excuse me, I write some sets of vectors and you tell me if the set is dependent or independent. Most often the adjective for this is linearly dependent or linearly independent, but just we are making it a little bit shorter and just calling it dependent or independent. So if I have 2, 4 and 3, 6, so this is my set. Let me call this set here, set S. Is this a dependent set or is it an independent set? Well, the numbers are small and friendly enough so that we can tell by looking. What do you think? Is this dependent or independent? Okay, that's your cue again. Of course, this is a dependent set. Like, I can build this out of that. If you want to call this one U and this one, call it V. Obviously, V is 1.5 times U, or 3/2 of U. Multiply this thing by 3/2, you get this one. Or typically have many choices. You can say U is equal to 2/3 of V. If I divide this thing by 3 and multiply by 2, I'll get that one. You can bring all of them to one side. For example, say 3u minus 2v is equal to 0. Okay, sometimes we can do by inspection. Are sets dependent or independent? We can do it just that easily. Sometimes it might not be that obvious. So for example, suppose I have the set S and it contains these three vectors: 1 2 0, 1 1 minus 1, 1 4 2. The question is S linearly dependent or linearly independent? And if they are linearly dependent, give the dependence. If so, give the dependence. If they are dependent, if such an equation applies to it, then make an example of it. Okay, there are two styles to approach this problem. Let's go after the one that is perhaps most informative. The way we go about it is by using this definition number 2. We make a linear combination, set it equal to 0, solve it. If at the end of our solution we find out all the coefficients are 0, well, then we call it independent. If there is anything else, we are going to call it dependent. So that's the style of how to handle these problems. So suppose I approach the problem like this: some multiple of the first vector, so 1 2 0, some coefficient, let's call coefficient number 1, coefficient number 2, you can call them x, y, z if you want to make it writing easier, coefficient number 3, 1 4 2. We set this equal to 0, so vector 0. One of two things happens. If we find out that C1, C2, C3 must be 0, that's the only way this can happen. We are going to call it linearly independent. If there is anything else, anything other than 0, we are going to call it linearly dependent. And that connection that we get is going to give us the dependence. How are they connected to each other? Well, how do we write this thing as an example of a Gauss-Jordan? Here we write 1 2 0, write second one 1 1 minus 1, 1 4 2. Right hand side is 0. We said when it's a homogeneous problem and right hand side is 0, whatever you do to it under Gauss-Jordan elimination, it just stays 0. So if you want to, you can eliminate this so that you just don't waste time writing zeros all over the place. Let me just continue with keeping them a couple of steps. You see that we are actually wasting time writing this. Okay, how do we go about Gauss-Jordan? So minus twice row 1 plus row 2 is going to eliminate this one. Well, that is already eliminated, so there is nothing to do here. There's nothing to do here, and so I get 1 1 1 0 minus twice that plus this is 0 minus twice this, and that becomes minus 1 minus twice this, and that it becomes a 2. And then now notice minus twice 0 plus 0 is 0. That's what I was referring to. Writing these zeros doesn't do anything for us. Well, you already see what's going on when we do the linear combination of these two. What happens? So I get minus row 2 plus row 3. Again, I have 1, 1, 1, and this 0, useless 0 here. Then I have 0, minus 1, 2, but this was 0 already. And when I subtract this from this row, 0, 0, 0, and of course subtracting 0 from 0, it just gives you 0. So again, nothing's happening here, but we're writing it. Okay, continuing from here, let's do complete Gauss Jordan. We insist on leading numbers to be 1, so I will have minus row 2, so that makes it 1, 1, 1, 0, 0, 1, minus 2, 0, and the fact that the last row got wiped out totally, it's the news that one of these vectors is going to be dependent on the others, and we are going to have that free parameter indicates that we have choices for C1, C2, C3 other than all of them being 0. Let's continue. I do minus row 2 plus row 1, so this becomes 1, 0, this becomes 3, 0, 1, minus 2, 0, 0, 0, 0, 0. Again, notice that it's just 0 on the right hand side. Writing in conventional notation, what this means is that C1 plus 3C3 is equal to 0, and C2 minus 2C3 is equal to 0, and there is nothing for here. So C3 can act as a parameter. C2 becomes 2C3, and C1 becomes minus 3C3. So if I go ahead and choose C3 any number, in this case any number other than 0, then C2 will be some number, C1 will be some number, and when those numbers are plugged here, we get a non-trivial combination. For example, if I take C3 to be 1, C2 according to this becomes 2, and C1 becomes minus 3. What this set means is that if I take minus 3 times the very first vector, 1, 2, 0, and 2 times the second vector, which is 1, 1, minus 1, and C3, which is 1 times 1, 4, 2, I indeed get 0. Let's verify. Is this really true? Minus 3 plus 2 plus 1 is 0. So the first one verifies. Minus 6 plus 2 plus 4, that is 0. This is 0. Minus 2 plus 2 is 0. So this is indeed true. So these three vectors, so what we get out of this problem is that these three we said this is linearly dependent, okay, because of this. Now if you want to go back to the original definition number 1, you can take one of these things to the one side and keep the other ones on the other side. That would be the first style of discussion. For example, if I want to isolate 1, 4, 2, I can say 1, 4, 2 can be built out of these two. Taking this to the other side means take 3 of these, like a cooking recipe. Take 3 of these things, and then when this goes to the other side, becomes minus 2 or whatever it is here. 1, 1, minus 1. So one of these things is a linear combination of the other two. Of course, once you have one of these relationship, you can drag any of these things to one side and leave the other ones to the other side. So for example, you can have 1, 1, 1, 1, 1, minus 1 is, well, I take this and I take the other ones to the other side, divide by 2, so it becomes minus 1/2. So this 1 goes to the right hand side, divides by 2, 1, 4, 2. 3 goes to the other side, minus 3 goes to the other side, becomes plus 3 divided by 2, 1, 1, excuse me, 1, 2, let me erase this, 1, 2, 0. And finally, if you want to give same opportunity to all of them, we took this one out here, we took this one out here, we can take 1, 2, 0. If you want 1, 2, 0, take that one to that side, keep these things, so it becomes 2/3 of 1, 1 minus 1 plus 1/3 of 1, 4, 2. So this one can be represented in terms of the other two, or if you want this one can be represented, or this one can be represented the other two. Of course, instead of wasting time like this, we can put it all in one equation and then take whoever you want to the other side, so long as all of these coefficients are not 0. We said that we call that the trivial combination. Of course, that is 0. That does not reveal any information for us. Okay, so so there are many problems related to this in your homeworks. We said there are two ideas, two approaches to this problem. Another approach is to take your vectors, write them as row vectors of a matrix, apply Gaussian elimination to make a echelon form. If at the bottom you end up with a set of zeros, then that is also an indication of linear dependence. However, you have to track things to see what is the dependence. So I'm going to leave that out because well, we already mentioned one way of doing this thing. Now, sometimes there are some easy ways of figuring out a set is dependent without going through all that work. So sometimes, based on some simple observation or some theorems, easy ways to detect dependence. There's no easy way of detecting independence, except for perhaps just 2 by 2 vectors. But case of dependence, there are some easy ways. First way, if you have a set of vectors, as many of these things as you want, as many dimensions as you want, if one of them happens to be 0, the set always turns out to be dependent. Well, let's put it in a kind of everyday language. If you have a person who doesn't do anything, well, adding him to any team that you have is just dead weight for the team, and you can take him out, still doesn't hurt anything. Same with the 0 vector. If you have a set that includes the 0 vector, the set becomes dependent. Let's see why. Let's show this thing by 0, and let's say this is vector u and this is vector v. Let's go ahead and make our definition. We said if I can write down some multiple of this plus a multiple of that plus multiple of that, that is 0. So if I can write such a equation with all of these numbers not being 0, then I have a dependent set. Can you come up with such a thing? Let me see. Maybe if I give you 1 second. This is kind of a silly question. So, well, yes, I can come up with an answer here. Just pick one of 0 vector and none of u vector and none of the v vector. Now my coefficients are not all 0 because one of them is 1. However, smartly enough, I picked the other ones equal to 0, so this is definitely 0, and it shows by our definition that the set is dependent. Okay, that is a bit of a cheap shot, but moving on, we have a next observation, that if you have more vectors than you have dimensions in your space, so if your number of vectors is more than dimension of the space, no, we haven't even defined what's the dimension, but it's just a number of elements that you have. Let me specify that with an example. So suppose I am in two-dimensional worlds like R2, that's just X and Y. If you pick more than 2 vectors in this, they definitely become dependent. So 3 vectors in R2, or to make it, to give yourself more room, 4 vectors in R2, and so on. These are always dependent. So set of 4 vectors and more, always dependent. So let's write an example. Suppose I give you a set with some ugly numbers, say 5 and 11, 75 and 23, and 15 minus 93, and so on. So okay, these vectors are in a two-dimensional space. They have 2 components. If I have more vectors than I have components, then they automatically gonna be dependent. It takes a little bit of a description to show why is that the case, but for now I'm gonna keep this lecture short and perhaps postpone it to certain future lecture. So if you have more, one way of thinking about it is like if you have a crowded situation, like too many people on a team, then some of them are going to be redundant and you can remove that. Now which one of them can be removed, that has to be investigated, but you know that at least one of them can be removed. If the number of vectors is more than the dimension of space, then we have dependence. Okay, these are 2 ways of telling that a set is dependent, and we come back to this issue perhaps later on. Okay, until next time, good luck and God bless.